So good evening. I will wait for a couple minutes, then I will start. Okay, so let me start. I hope my screen is visible. So today I will be going to discuss some, obviously the assignment 4 questions, and as well as I will solve certain problems and discuss some particular topics which will help you all to solve uh, the problems of assignment 5. And so those questions related to that I have tried to give. So initially I will start with the assignment questions and discuss the assignment first. So this is the assignment. Okay, so the first question is about the hypsometric relation or the equation. So the question is, the hypsometric relation or equation can be used to find, so it has been said that the thickness between two pressure surfaces, pressure difference between two layers, and the mean temperature. So the answer should be all of the above. So why the answer is all of the above? So let me write here. So the hypsometric equation is a simple geopotential height equation which tells that the Z or the delta Z between two pressure surfaces will be given by R, the specific gas constant. Mostly we take the dry air gas constant, and the mean temperature of the column in kelvins divided by the gravity log of, you have P1 by P2, where P1 is the lower pressure surface and P2 is the upper pressure surface. It can be any surface, 1500, then it can be 700, 500, like that. So it is upper pressure surface. So as per the question, you can see that the height between two pressure levels can be found. T bar, that is the mean temperature of the column, that can be also found. And the third thing is that, wait, we go to that. Yes, the thickness between two pressure surface and the pressure differences. So P0 and P1, if you can find, then if one pressure layer is known, then we can easily find out. So all of the above should be the correct answer. Okay, let me switch off the video because network is poor. Okay. So the next question is, what is the thickness of the dry air between 1000 and 500 millibar surfaces having mean temperature of 5 degrees Celsius? So in this question, we will solve this question because it's a numerical problem. I have given it separately. Let us discuss first the theoretical questions and the conceptual questions first. Third question represents, in gas equation, Pc is equal to RT, the parameter C is known as. So let me again write it here. What has been given? Pc is equal RT. Now remember the ideal gas equation which I have discussed in the second lecture. There I have written ideal gas in three ways. One is PV is equal mu R star T. Second thing is P alpha is equal RT. Third is P is equal rho RT. So these three ways we have written the ideal gas equation. Now compare with this equation, we can easily find out that this is matching. Therefore C should be equal to alpha. And what we defined alpha? Alpha is the specific volume. And what is the meaning of the specific? Means per unit mass. So this is volume per unit mass. That's all. Therefore, that question's answer should be specific volume. Okay. Fourth question is, in thermodynamics, a closed system is a type of thermodynamic system where dash is or are conserved within the boundaries of the system. So the actual answer should be the mass. Why? Because even if you have a closed thermodynamical system, matters cannot pass this particular layer, but the energy can be radiated out. The closed system's definition is like that. So if the energy can be radiated out, then it cannot, means the energy cannot be remaining same. Therefore, The answer should be only mass which is conserved, not energy. Okay. The apparent molecular weight of dry air is, we have solved it in the second problem solving session. You can refer to that. We have a table of several gases which are present. All are dry gases, not vapor, and its percentage contribution and molar masses. Based on that, just we use the mean molecular mass formula and we can get 28.97. I have solved it in details. Okay, the next is also a numerical, so we will solve. Seventh is the density of the moist air is dash the density of dry air for same volume. Well, so density is mass per unit volume, but let us consider 1 mole of moist air and 1 mole of dry air. I know the molar mass of moist air is 28.93. In the previous problem solving session I have solved this. So it is this. This is the molar mass, gram per mole. And dry air is 28.97, which we have seen now and also have discussed. So 1 mole of moist air is this. So you can see that for 1 mole of gas and for same volume, if this mass so this 1 mole of moist air, this is 28.93, and for dry air it is 28.97. So for same volume, we can easily say that the moist air's mass of the moist air is less than the mass of the dry air. So density of moist air is always less than mass or density of dry air. So the correct option will be density of moist air is less than the density of the dry air. Fine. This is also an interesting question, the 8th one. I will solve it. The ratio of the gas constant for dry air to moist air is, we have solved it, but I can again explain. And this is also a numerical problem. 11th is the same. 12 is also the same. So we will see this. Okay. First is that RD by RV. So we have already calculated that RD is nothing but R star by MD. And this comes out to be about 287 joules per Kelvin per kg, where MD we take as 28.97 grams per mole. And RV is R star by MV, where MV is the mass of the vapor. We take 18 grams per mole, and its value is 461.5 joules per Kelvin per kg. And you have been asked to calculate the ratio of RD by RV, and it comes out to be 287 divided by 461.5. So if you do it, it comes out to be nearly equal to 0.622. So the correct option will be 0.622. Fine. This all conceptual and theoretical question I have already done. The next thing is the numericals corresponding to this assignment. So the first question is, what is the thickness of dry air between 1000 and 500 millibar surfaces having mean temperature of 5 degrees Celsius? Now here in this atmosphere, you take any temperature, but you have to convert it into Kelvin, because in the thermodynamics we always convert any degree Celsius or any Fahrenheit thing to Kelvin, because that is the standard unit. Fine. Now it has been asked to calculate the thickness of the dry air. So how to calculate the thickness of the dry air? Only one equation we know which can calculate this, that is the hypsometric equation. So using the hypsometric equation, delta Z, the thickness between the any two pressure levels. So suppose this is 500, this is 1000. Any column you take, and here temperature given to be 5 degrees Celsius. This is the mean temperature over the entire column. Each place it will have different temperature. Okay, so delta Z, I will write the formula. That will be RD T bar by G log of P naught by P. P naught is the lower pressure, lower surface pressure, and P is the upper surface pressure. Fine. Now T bar is given to be 5 degrees Celsius. So 5 degrees Celsius will be how much? 5 plus 273, that is 278 Kelvin. So the temperature is known, this T bar is now known, G is already known, RD is known, that is 287. The P naught and P are also known. So you can easily calculate the thickness between the two pressure surfaces. So it will be delta Z will be equal to 287 into 278 divided by 9.81 log of 1000 by 500. So this will be 2. Log 2 is about 0.6993. So 287 into 278 divided by 9.81 into 0.6993. So if you calculate, let me calculate it, divided by 9.81, it comes out to be about 5637.4 meters, which is very near to one answer, I think 5643 meters. So that is the correct option. So whenever this thickness between the dry air between 1000 and 500 millibar or any two pressure surface is given, hypsometric equation is the best equation to be used. And if lapse rates are given, then the hypsometric equation changes. So we have to use that. Okay. This question someone has asked in the problem solving session 2, but I couldn't solve because it's an assignment question. Now I can solve, but I have given the hint in the previous session. Okay, so here it has been said that if at 0 degrees Celsius, again, see this is a temperature, so you have to convert it into Kelvin. 0 degrees Celsius, the density of dry air is given, therefore rho d is 1.275 kg per meter cube, and the density of the water vapor alone is 4.77. Rho v I am writing vapor 4.77 into 10 to the power minus 3 kg per meter cube. What is the total pressure exerted by a mixture of dry air and water vapor? So this mixture of dry air and water vapor and what will be the total pressure will be given by the Dalton's law of partial pressure. So we will use that Dalton's law of partial pressure. That is, total pressure is the sum of the partial pressure if the volume remains same. So in a column, I would say the volume will remain same. It will have both dry plus vapors. So total pressure which is exerting here is, say, P will be equal to pressure due to dry air and pressure due to vapor. This is pressure due to dry air and this is pressure due to vapor. Now, how to calculate this dry air pressure and vapor pressure? Well, we know that the temperature is given. If temperature is given, it's very easy to calculate the pressure. How? Now, there is ideal gas equation. So, what is that ideal gas? For dry air, it is PD is equal to rho d RD into T. So three forms of ideal gas I was written in the earlier slide. P is equal to rho RT can be one, P alpha is equal to RT, and PV is equal to mu R star T, where R star is the actual, that universal gas constant. These are specific. So I am using this, and E will be there for what? Rho V RV into T. T is given to be 0 degrees Celsius, which can be converted to Kelvin. So just calculate it. PD will be equal to therefore 1.275 into 287 into 273, right? And E will be therefore 4.77 into 10 to the power minus 3 into 461.5, because RV is that, into 273. So you add it, the P will be equal to the entire thing PD which I have written and E I have written. So if you add it, it comes out to be 998.97 as the dry air pressure, and this vapor pressure comes out to be 600.96. So if you add both, it comes out to be about 1004.97.9. This is in pascals. So in hectopascal it will be 1004.9, which is close to 1005. So one thing to note here is that dry air is exerting maximum pressure as compared to the vapors. Fine. So the solution here is 1005 hectopascals. Okay. Now this is a very good question. This is an extremely important question because it's a long kind of question. So let's read it. If the ratio of the number density of the oxygen atoms to the number density of hydrogen atoms at a geopotential height of 200 km above the Earth's surface is 10 to the power 5. Calculate the ratio of the number densities of these two constituents, same that your oxygen to hydrogen, at geopotential height of 1400 kilometers. Now assume an isothermal atmosphere at between 200 and 1400. So mean column temperature is constant, that is 2000 Kelvin, and here now it is Kelvin given. We don't need to convert. Okay. So for that, first what is given, let us write. So this is, suppose number density is denoted by N. So N of oxygen to N of hydrogen at your 200 kilometer is given to be 10 to the power 5. Fine. And it has also been given that temperature, mean temperature, the mean temperature is about 2000 Kelvin. This is also given. Now I need to find out number density of oxygen to number density of hydrogen at 1400 kilometers. This is what I need to find. But before that, ideal gas law using kinetic theory of gases is written as PV is equal N kBT, where kB is the Boltzmann constant. kB is the Boltzmann constant, T is the temperature of the gas, P and V are known, N is the number of molecules or atoms, what it is. Now what we have seen is PV is equal mu R star T. Now this mu can be written as N by Na, this is because the definition of moles, number of moles, into R star into T. Now this P is equal N by V into R star by Na into T. Now this R star, as per this kinetic theory of gases, can be written as Na into Kb. Right? So this will be now N Kb into T, because if you put R star as Na Kb, Na cancels out, so N Kb T. Therefore we can see if T is constant, because it's given isothermal atmosphere, so pressure is proportional to the your number density. of a particular atom or gas kind. So P is proportional to N. Therefore, whatever we are writing like this, we can change it to this. So it will be P of oxygen to P of hydrogen at 200 is nothing but 10 to the power 5 because it's a ratio. We can write. And what we need to find out is PO by pH at 1400 is what? Because that will be nothing but equal to N of O by N of H at 1400. Right? So this is the first step. The second step is, so let me write this as the first. Second step is, we know that P at any lower height will be equal to P at some P1 is at a higher height and P0 is that reference which is at the lower height, will be equal to e to the power minus delta Z by H, and this P2 will be equal to P0 e to the power minus delta Z by H. Now this will be H2, this will be H1. Fine. Now similarly we will write it for hydrogen and oxygen. So P of hydrogen at 1400 will be equal to P of hydrogen at 200 e to the power minus, I am writing delta Z, but delta Z we know will be 1400 minus 200 kilometers. So it will be 1200 kilometers. This we know. Delta Z divided by, now this will be H of hydrogen. H is scale height. Similarly, P of oxygen at 1400 kilometer will be equal to P of oxygen at 200 kilometers e to the power minus delta Z remain to be same by H of O. Now if we divide this thing, then what we will get? Or better, this I write this as some A, this equation as B, and go to the next page. So if we now do B by A, such that oxygen is at the numerator and hydrogen is at the denominator. So what I will get is P oxygen by P hydrogen at 1400 will be equal to P oxygen by P hydrogen at 200 e to the power minus delta Z into 1 by H of oxygen minus 1 by H of hydrogen. This will be there. Okay. Now remember this P0 by pH is nothing but N0 by H, NO by H. That is the density, number density, because pressure is proportional to number density. And if you are in the dividing case, then it can be written. Fine. What is required to know now here is this H0 and HH. So let us calculate. We know the formula of scale height. So what is scale height? Scale height H, any H, will be equal to RD T bar by G. Now this RD is for the dry gas. This RD is for the dry gas. Now for hydrogen HH, it will be R of H, and how will we find out the RH? This will be R star by the molar mass of hydrogen into T bar by G. Fine. So this will be 8314 divided by hydrogen atoms mass is 1 grams per mole. So 1, I have divided above into 1000 already because it is in grams, we have to convert it to kg, into 2000 Kelvin divided by 9.81. And if you do it, it will come out to be about 1.695 into 10 to the power 6 meters, or you can write 1.695 into 10 cube kilometers, because delta z is in kilometers I have, so why to do in meters. Another is for oxygen, that will be R star by MO into T bar by G. Now R star again is, see, R star is 8.314. Now M0 will be, for oxygen is 16 grams per mole. So since it is in grams, I will multiply above with 1000 and below with 1000. So it will be 8314 divided by 16. Just only above you have to multiply, because grams bar 1000 is actually kg. So this should be 2000 divided by 9.81. Now if you calculate this, it comes out to be about 0.1059 into 10 to the power 6 meters, or you can write 0.1059 into 10 cube kilometers. Now this scale heights we have found out. Now just we need to do this bracketed thing expression, that is what, 1 by HO minus 1 by HH. Now you can see clearly that HO is much smaller than HH. So if 1 by HO, therefore must be greater than 1 by HH. It is expected. So what I do is that this 10 to the power minus 3 I will be at the top, because 10 cube is in the denominator. You can try this calculation, it's easy. 1059 minus 1 upon 1.695. If you calculate, it comes out to be about 8.852 into 10 to the power minus 3. Fine. And here a delta z is to be multiplied. So I write this equation here. So it will be PO by PH of 1400 will be equal to PO by PH at 200 e to the power minus 1200 kilometers into 8.852 into 10 to the power minus 3. If you calculate properly, so this is also known, this is nothing but NO by NH at 100, and if you calculate this thing out, it comes out to be minus 10.6, and this is NO by NH at 1400 kilometers. Now this is known. What is this? 10 to the power 5, already given in the question. So 10 to the power 5 e to the power minus 10.6, you come out to be about 2.5. So the answer of number density of oxygen atom to number density of hydrogen atom at 1400 kilometers is about 2.5. This is the answer. So it's a long question, but very fundamental and very good question to attempt. Fine. The next thing is, just a minute. Yes. Okay. Calculate the geopotential height of 1000 hectopascals pressure surface when the pressure at sea level is 1014 hectopascals. The scale height of the atmosphere may be taken as 8 kilometer. So it will be answer above sea level, it's fine. So answer above sea level means this 1014 hectopascals, as it has been already showed here, that this is the surface, means the sea level pressure. So sea level pressure is this. So I will put this as Z is equal to 0, corresponding to Z is equal to 0, this is the pressure. Okay, so the geopotential height at 1000 hectopascals, again by simple that hypsometric equation, or using hypsometric equation you can also always find out. So this will be RD. T bar is not given. So what I do is that, let me write it. This is nothing but the scale height, right? So we can easily do it. The log of 1014. The reference will be at the top, 1000 will be at the bottom. That's all. So you get, this is nothing but the scale height. So this is given to be 8 kilometers. Log of 1014 by 1000. So Z at 1000 can be easily found out now. You calculate it out, it comes out to be about 0.11. So, and that is the answer, I think. Or what you can do is that the same thing, just in the other way. So is equal to P is equal to P naught e to the power minus Z by H. The same equation comes from this particular equation. So you just put the values of H as 8 kilometers and P by P naught is known. So ultimately this is coming 0.111 kilometers. Fine. Okay. Now the next question is, what is the pressure exerted by water vapor at 273 Kelvin having the density 4.77 grams per meter cube? Remember, this is not the SI unit. And we have already calculated this particular thing in the previous one of the questions. Okay, so but this is not in kilograms per meter cube. So you convert it into kilograms per meter cube. How to do that? Simple, 4.77 grams to kilogram into 10 to the power minus 3 kg per meter cube. Fine. Now 273 Kelvin is already known to us. What is the pressure? We need to find out. So only thing is that the ideal gas equation, which will come into your mind. Ideal gas equation is nothing but P is equal to rho RT, right? And for vapor, we already know what is the specific gas constant. Therefore, this I write it E. This is nothing but the vapor pressure. Vapor pressure in atmospheric science is always written in terms of E. So this will be equal to rho V RV into T. So what is rho V? 4.77 into 10 to the power minus 3 kg per meter cube. RV is known, 461.5 joules per Kelvin per kg, because it is for the vapors, and T is 273 Kelvin. If you calculate it out, it comes out to be about 600.96 pascals and can be written as 6 hectopascal or nearly 6 millibar. So this is the answer. I think 6.01 is there in the assignment. So that is the answer. Okay. This next question is quite similar. I have already solved one of the question in the previous problem solving session, where carbon dioxide and I think nitrogen gas are used to find out what is the mean molecular mass of these two constituents if are there in the atmosphere, total 100%. Now here it is said that oxygen and nitrogen are distributed to be 79% and 21%. Well, I think that it should be that oxygen should be 21% and nitrogen should be 79%. Then only we can get the answer. If we take oxygen to be 79% and nitrogen to be 21%, then we will get much greater value, which is not there in the option at all. So what I believe is oxygen is 21%, nitrogen is 79%. You can try the other way, and I don't think the answer will match. It will be more than 32. Fine. Let's do it. So mean molecular mass, again I am writing the formula. So it's summation. Okay. Oh. summation, some I, the molar mass of that ith gas into its percentage contribution of I divided by summation I percentage contribution. So the sum total of all the percentage contribution. Fine. Now m bar, the mean molecular mass. But before that, oxygen's molar mass is how much? MO2, that is 2 into 16, that is 32 grams per mole. Again, mass of nitrogen is 2 into 14, that is 28 grams per mole. Right? Therefore, m bar will be equal to the mass of oxygen into percentage contribution of oxygen plus mass of nitrogen into percentage contribution of nitrogen divided by total contribution is 100% because 79 plus 21 will always be 100%. Therefore, m bar will be equal to MO2 is 32, MO2 is 32, and your percentage contribution according to me should be 21 plus the molar mass of N2, that is 28 into 79 divided by 100. Now if you do it, I think you will get, let me do it, 32 into 21 is about 672 plus 28 into 79, 2884 divided by 100. So its answer comes out to be about 28.84. Maybe this is the answer or very near to that this answer is present. So therefore oxygen should be 21%, nitrogen should be 79%. Had it been opposite, then I think the answer should go more than 32 because oxygen's contribution is only 79%. So oxygen's molar mass is 32, so it should be always greater than. This is the answer. But you have to follow this. Now I think that the assignment questions are now over. Now I will give certain questions which will help to improve your concept for the week 5 problems which are there in the assignments, which are very less problems are present, so you can attempt those. Okay. So here the question is given that if the mixing ratio of the air parcel is 2 grams per kg, the total pressure is 1020 MB, then what is the vapor pressure? Fine. Now, what is mixing ratio? Mixing ratio, I denote it by R. People generally do it by W, so I denote it with R. That will be given, that is 2 grams per kg. That is 2 grams of water vapor in 1000 grams of dry air. See, this is 1 kg, so 1 kg of dry air. So from 1000 grams of dry air, 2 grams of water is present or vapor is present. So it is 2 grams per kg. So let us write it in SI units, which does not have any unit because it is mass per mass. It will be about 0.002. Okay, this is the mixing ratio. Total pressure is given to be 1020 millibar, and I need to find out the vapor pressure, that is E. How to find out? Now see, R, the mixing ratio, is defined as density of vapor to that of the density of dry air. Now density of vapor using ideal gas equation, we can write it as E by RVT. And what is rho d? PD, the dry air, upon RDT. Now see, this TT can be chopped out. Now this E and PD left. Now RD by RV. RD's value we know, 287. RV's value we know 461.5, and we just now have calculated this value to be 0.622 into E by PT. Okay. Now we have already seen that the total pressure is pressure by dry air plus pressure by vapor, and I have already known that this E is very small than PT. Therefore P, the total pressure, can be approximately equal to PD. That is what we use here. Therefore R can be written as 0.622. Sometimes this 0.622 is denoted as epsilon. So this is E by PD. P. Okay. R will be equal to epsilon E by P. This is the formula of the mixing ratio. Now we need to find out E. Therefore E will be equal to R into P divided by epsilon. So what is R? 0.002. What is your P? 1020. Don't need to convert the millibars into pascals, because ultimately the E will come in millibars. It's fine. Divided by 0.622. Now if we calculate it, it will come around 3.279 millibar. So you can see that it is very small, but the vapor pressure is this. So this is how to calculate the vapor pressure if all these things are given. I think this kind of question is there in the assignment 5, which is very easy. You can do it. Okay. This is somewhat different. This is somewhat different based on the concept of virtual temperature, and I will solve this question now. Okay. Okay. Now before proceeding to this question, I will again discuss just the formula of virtual temperature and a simplification of this virtual temperature formulation. So virtual temperature I have already derived in the previous problem solving session, that is equal to temperature into 1 plus R by epsilon divided by 1 plus R. What is R? Again I am writing, this is the mixing ratio, which nothing but indicates how much amount of vapor or mass of vapor is present in 1000 grams of dry air. That's all. What is epsilon? Epsilon is 0.622. Just now we have seen, that is RD by RV. Fine. Now we will do some very short simplification. Okay. Now this 1 by epsilon can be written as 1.609. 1.609, because 1 by 0.622, if you do, it's nearly coming to this. Okay. Now this divided by 1 plus R, right? Okay. Now what I do is that T into 1 plus 1.609 R, and I will keep the denominator in the numerator as this 1 plus R to the power minus 1. Now expand this binomially and neglect higher order terms. Okay. So it will come out to be T into 1 plus 1.609 R into 1 minus R. That's all. The R square terms I will not take. So it will be TV into 1 minus R plus 1.609 R minus 1.609 R square. This R square term is also very small, because R you have seen it's about 0.00 something 2. So for example, it is very small, so it's not required. Only up to this term we will take. Therefore, sorry, this is T, this is TV. The original temperature is T, the dry air temperature is T, so it will be 1 plus 0.9 nearly 0.61 R. Therefore, virtual temperature is this. We can write virtual temperature or calculate virtual temperature using this. Now you see the question what is being given here. Correction for the moist air. Okay, temperature correction. What is temperature correction? This virtual temperature correction is delta T, and that is equal to TV minus T. Fine. And TV minus T we can calculate from here. Delta T will be equal to TV minus T, and that will be equal to 0.61 R into T. Right? So T is 303 Kelvin, because we have to convert it into kelvins. Okay, so this is there, and you have R, that is 20 grams per kg, which is nothing but 0.02. Right, just place and get the result. So it is 0.61 into 0.02 into 303, and what you will get is about 3.69 Kelvin. So this is the answer. Okay. So here we have seen the virtual temperature correction, how to make, and virtual temperature's formula, if you have to calculate any numerical based on, of course, the mixing ratio should be given, then only you can calculate the virtual temperature. And then we have seen that what you call your, how to calculate the virtual temperature correction based on if the mixing ratio and all the other things are given. Now this is a very standard kind of question. Calculate the work done in compressing isothermally 2 kg of dry air to 1/10 of its volume. This is already a kind of an 11-12 level question. Just you have to calculate the isothermal work done, because it is same temperature, 15 degrees Celsius, and it has been given that 2 kg of dry air to 1/10 of its volume. Fine. Now, what we will do is that we know that, just derive the work done, what is there. P, let us write it, P alpha is equal to RT. Right? Or we can, yes, fine. P alpha is equal to RT. Now, P will be equal to RT by alpha. So it's a dry air, so you can just put this to be RT. Fine. And let us for a time being just take only dry air. Also it is given. Now work done is given by what? PD alpha, where we are taking only the work done per unit mass. So it's a specific work, you can say. Okay. So this is per kg. Is the amount of work done. Okay. So PD alpha. Now, actually the work done's definition is PDV from V1 to V2. Actual work done's definition is PDV from V1 to V2. Now here we are taking it from alpha 1 to alpha 2, because alpha is nothing but volume per unit mass. Alpha is nothing but volume per unit mass. So P we already have seen, that is RT by alpha, P alpha. Simple. T is constant, R is also constant for dry air, so it will be, now what has been said is, okay fine, let me write it now, alpha 2 and alpha 1, and alpha 2 is alpha 1 by 10, alpha 2 is alpha 1 by 10, because 1/10 of its initial volume. Fine. Now RD is about 287. Temperature at 15 degrees Celsius is nothing but 288 Kelvin. This is 288 Kelvin divided by, let us not write this because d alpha by alpha is there, that will give us log alpha, 287 into 288 log of alpha 2 by alpha 1, and that will come out to be 288 into log of 1 by 10. Oh, sorry. So this will be this. Okay. So now, so 287 into 288, if you calculate this entire thing, it will be a negative 19322.4 joules per kg. Fine. So this will be minus 190.322 or 32 kg per kilojoules per kg. Just 10 to the power minus 3 we have taken. Now this is for 1 kg. So it is work done for 1 kg. Right? So for 2 kg, just multiply it with 2. So 2 into 190.32. So whatever will be the answer. And this is that isothermal compression kind of. That's why negative. Right. So this is the question. And okay. Next is the question of specific humidity. Specific humidity of a sample of air. So what is specific humidity? Specific humidity Q is nothing but density of vapor to that of density of vapor plus density of dry air. And density of dry air, density of dry air is much greater than density of vapor. We have seen 10 to the power minus 3, and this is normal 1.28 and something like that. So if it is high, then Q can be approximated as rho V by rho D, and that is nothing but mixing ratio. So mixing ratio and specific humidity denotes the same thing. In your calculation, you can use same formula of R which we have derived in the previous question, that is epsilon E by P, and this P can be PD or the total pressure. We have seen because PD is much greater than E. Okay. Specific humidity is given, so given Q is equal to 0.0196, right? No units because it is like that, same as the mixing ratio. Temperature is given, that is about 30 degrees Celsius, that is 303 Kelvin. Find its virtual temperature. So how will we find? I know that Q is equal to R. Okay. So if Q is equal to R, and we know the virtual temperature formula as TV is equal to T 1 plus 0.61 into R. Just put the value and get the result. Fine. So T is what? 303. 1 plus 0.61 into what is that? 0.00196. So if you calculate, let's see how much it comes. Just a minute. 0.61 into 0.0196 plus 1 into 303. It's about 306.6 Kelvin. Right? And another second part of the question, if the total pressure of the moist air is 1014 hectopascals, what is its density? Fine, we can easily get it. First is, for the second part, let me go after, okay fine, here let me write here. So total pressure P is 1014 hectopascals. Now Q, as I have said, that equal to R, that is epsilon E by P, that is 0.622 into E by 1014, and Q is also already known. So I come here, what is Q? 0.0196. You multiply it with 1014, divide it with 0.622, that is equal to E, and E comes out to be about 31.95 hectopascals, right? So this is E. Now use ideal gas equation, because I know what is the temperature. Use ideal gas equation, it's simple. So rho V will be nothing but E by RVT. Just put it, but remember, this is rho V, which will be calculated in kg per meter cube. So you have to convert this E from hectopascals to pascals. So what is that? 3195, that's just 100 multiplication divided by 461.5 into T, that is 303. So what it will come, let me calculate. 31.95 divided by 461.5 divided by 303. It comes out to be about 2.28 into 10 to the power minus 4 kg per meter cube. So you can see again the vapor's density is very low. Okay. Fine. Or the total density, if you have to find out, you have P is equal to rho R into T. You take it RD for your simplicity. So what it will give? Rho will be 1014.00 divided by 287 into 303. What it will give? Let's see. So it's 1014.00, because it has said that what is its density. So moist air's density can be the total, right? Divided by 287 divided by 303. About 1.16, which is fine, kg per meter cube, right? This is the total density. And why have we used RD? Because it's fine, because dry air's composition is much greater. Fine. Or what you can say is that here RD, if you are putting, you can write it as virtual temperature, because we have seen for moist air, this is what is happening. So for moist air, PM is equal to rho m RD into TV, or you write RM into T. So let us write this as 306 or 30, okay fine, 306 is fine. So let us recalculate it and write the actual result. Let me erase this particular thing. Wait. It is there. Okay. So it will be 306.6, and it comes out to be, let's see, 1014.00 divided by 287 divided by 306.6. It comes out to be 1.15 kg per meter. This is the density of moist air. Okay. Fine. The next question is a parcel of moist air has a total pressure of 975 hectopascals and a temperature of 15 degrees Celsius. If the mixing ratio is 1.80 grams per kg. What are the water vapor pressure and the virtual temperature? It's simple, just like the previous question, it has been said. Well, so let's calculate it. First of all, we can calculate the virtual temperature because this is given. R is also given. So let us write what is given. So given is R mixing ratio, that is 1.8 grams per kg, and how much it will be? 0.0018, right? Temperature is given, is 15 degrees Celsius, which is nothing but 273 plus 15, that is 288 Kelvin, right? Total pressure, total pressure of the moisture is given to be 975 hectopascals. I need to find out the vapor pressure and the virtual temperature. So just write the virtual temperature formulation, that is TV is equal to T 1 plus 0.61 into R. So that will be 288 1 plus 0.61 into R, that is 0.0018. So it will be 288 1 plus, let me calculate it, okay, it comes out to be about, let me not write this, it comes out to be about 288.3. It's about 288.3 Kelvin, very small change. Fine. Now vapor pressure can be found out using the in the formula of R. So R will be equal to epsilon E by P. So E therefore will be Rp by epsilon. So R is what? 0.0018. P is what? 975 divided by oh, I'm sorry, I think something, no, it's okay, 0.622, and that comes out to be about 2.82 millibars or hectopascals, whatever you say. So this is the answer. So a same kind of question I have solved here. This will help to understand the concepts for solving the assignments. Now I will talk about the concept of specific heat capacities, how this specific heat for the dry air, for the vapors is we can find out, that we will see, and then we'll do some questions based on potential temperature and dry static and moist static energy. Not much questions are left, just I think 2 questions, maybe 1, 2, 3. 3 questions are there. Okay. Fine. So the concept of Cp and Cv. Well, so again see, these are the specific heat. Sorry. Just a minute. Okay, here we have. So this is the specific, means per unit mass. So heat capacity is per unit mass. If we define what is the heat capacity, it is the amount of heat per unit mass given to, or amount of heat given to 1 kg of mass or a substance to increase its temperature, the body's temperature, by 1 degree Celsius or 1 degree Kelvin, because it's the temperature change. Temperature change can be in degree Celsius or can be in Kelvin, linear scale. Now how to derive these Cp and Cv and what are their values? Because somewhere it is written that Cp is about 1005 joules per Kelvin per kg. CV is 718 joules per Kelvin per kg for dry air. So why and how these are coming? Or in general, in molar kind of theory, per unit mole if you go, or in case of heat capacities, how it has originated. So it has originated again from the kinetic theory of gases, which a famous law known as the law of equipartition of energy. Law of equipartition of energy. What does it say? It says that each degree of freedom will acquire equal amount of energy, that is half kBt. So half kBt amount of energy will be given to each degrees of freedom. So let us consider the case of a monoatomic gas, which in our atmosphere is very less. Chance of diatomic gases are much more. So monoatomic gas, if you see, it will have whatever degrees of freedom, 3, right? 3 translational degrees of freedom. That's all. So for one molecule, or not, it will be not a molecule, it will be one atom. So for one atom, kinetic energy is nothing but CVT. CV is the heat capacity at constant volume. This is how it is defined. Okay, that will be equal to, therefore, see, 3 degrees of freedom, so 3 into half kBt. This is the amount of kinetic energy. So it will be 3 by 2 kBt. Therefore CV will be what? 3 by 2 kB. Right? Now this is for one atom. Now for N or Na atoms, what will happen? CV will be equal to 3 by 2 Na into Kb, and nothing but is Na and Kb is nothing but R star, the universal gas constant. So for CV, that is for mole, is 3 by 2 R star. It is joules per Kelvin per mole, right? Because we are dealing with mole. Fine. Now, or atomic level or kind of that. Fine. Next is for diatomic gases. I will not do for triatomic gases, just for diatomic gases. You people all know these things. So diatomic gases, degree of freedom is 5. So again for one molecule now, it will be Ke is equal to CVT, that is equal to, now 5 degrees of freedom, 3 translation, 2 vibration. So that will be kBt. Now for Na molecule, this will be 5 by 2 R star, that is equal to CV. Okay. And if you do Cp minus Cv, this is equal to R star, which we know for 1 mole. This is for 1 mole. Okay. For 2 moles, it will be 2 R star. Fine. So you can see that Cp from this equation, Cp will be equal to R star plus Cv. So for diatomic gases, it will be 7 by 2 R star, which can be written as 5 by 2 plus 1 R star. That's all. So Cp is 7 by 2 R star. So for diatomic gas, Cp is 7 by 2 R star for 1 mole. Cv is 5 by 2 R star for 1 mole. So these are all for 1 mole for diatomic gas. Right? Okay. Now, for dry air, let me write. For dry air, now we know that atmosphere consists of dry air and vapor. So for dry air, Rd becomes what? R star by Md. Right? Now, CPD, therefore, that is now Earlier it was joules per Kelvin per mole. We are considering per unit mole, but now here per unit kg specific. Okay, so now CPD for dry air will be how much? It will be, earlier it was 7 by 2 R star, now it will be 7 by 2, just replace it with RD, or you just write it, or I will just chop it out, R star by MD, because this is per unit mass. Okay, so it will be 7 by 2 RD. How much it comes? Let's see, 7 by 2 into, we know this value, 287. How much it comes? Let's see. Is it near 1004? Let's see. 287 divided by 2. Yes, it is 1004.5. So it is joules per Kelvin per kg. Earlier it was joules per Kelvin per mole. Fine. Similarly, CVD will be equal to 5 by 2 R star. This is per unit mole. Now if I divide it with the molar mass, which is having grams per mole, MV, it comes out to be 5 by 2 R, sorry, this is D. So it will be RT. So it will be 5 by 2 into 287. Let's calculate. Let's see whether it is coming near 718 or not. 287 divided by 2. 717.5. Right? So this is joules per Kelvin per kg. Now, if I do CPD minus CVD, that is for 1 kg of gas, how much it comes? It is 1004.5 minus 717.5, you get 287, which it should be, because 7 by 2 minus 5 by 2 is 1 RD. So that is joules per Kelvin per kg. So this thing is valid here also for specific term, that CPD minus CPD minus CVD will be equal to RT. Similarly for vapors, let us calculate. So for vapors, well, for moist states it will be different, it will somewhat different, but for vapors, for moist air you will get some terms of mixing ratios, and I am not going into that details because that is not covered also. So for vapors, we have now just replace CPV as 7 by 2 R star by MV, right? And that comes out to be 7 by 2 into 461.5. And if you do it, it comes out to be 1615.2 joules per Kelvin per kg. Similarly, CVV will be 5 by 2 R star by MV, and that comes out to be 5 by 2 into 461.5. That comes out to be 1153.75 joules per Kelvin per kg. Again, if you subtract it, it comes out to be about 461.5, right? Okay, this is another thing. And another thing is that gamma is Cp by Cv. This is gamma. So you can see that for monoatomic gas, it is Cp is what? For monoatomic gas, it will be about 5 by 2, so it will be 5 by 3. And for gamma diatomic gas, it will be 7 by 5. And I think for triatomic form, triatomic gas, it will be 9 by 7. This you should remember, some variant you can use. Okay. So this is the concept of specific heat capacities I'm trying to give in here. Okay. Next is a question based on potential temperature. This potential temperature and equivalent potential temperature are very important concept. So I will solve the derivation of the potential temperature, and we'll say what happens, what is the potential temperature, what is the concept behind potential temperature, what is the concept behind the equivalent potential temperature. So this thing I will explain now and solve some question. I think 2 questions based on potential temperature is left, and one related to the dry static energy and moist static energy is also there. Okay. Now, here we have an air parcel, right? Now let me give you some insight. What happens when an air parcel goes up? Suppose by some mechanism it is going up. Suppose this is the surface, there is an air parcel. It need not to be spherical, it can be any shape, it can be a point. Nearly a small volume it is capturing. No heat is transferred. No heat is transferred outside, no mass is exchanged. So it is an adiabatic process. Fine. And there are some list of points which you have to remember using this parcel theory, that environment is in hydrostatic approximation, that is dP is equal to minus rho g dz. You can apply there in the environment, not in the parcel. Okay. And at any level pressure should be same. So at any level, suppose here, so by some mechanism, maybe some convergence of air, this parcel has lifted up, and at some level it is here. Okay. Now here inside pressure and outside pressure should be same. This is the theory. This is the based on which the air parcel theory is based. So pressure outside should be equal to pressure inside. If pressure outside should be equal to pressure inside, then as we know that P is inversely related to the volume in case of ideal gas law. If temperature, although it is decreasing, but still to have the same pressure outside, it will increase its volume. So if it increases its volume, how it will increase? It will increase, so it will increase the volume by doing some work, and this work done will lose some energy. And why is it losing energy? Now if it is losing energy, if kinetic energy is losing, then temperature dips down. So as the parcel goes up, temperature decreases. Fine. Okay. Now that's why we talk about the gamma, the lapse rate, not the gamma which I have shown in the earlier slide. That is Cp by Cv ratio. Okay. But this gamma is the lapse rate. This gamma is for the lapse rate. Fine. This is the actual thing which is going on in the atmosphere. If we take a portion of the atmosphere and follow that as a parcel which is moving adiabatically, then so in the adiabatic process we know that PV to the power gamma is constant. This gamma is that ratio of Cp by Cv, not the lapse rate. Okay, so P is inversely proportional to the volume. So pressure if decreases, suppose outside the pressure is decreasing, of course as we go up in the height pressure is decreasing, so the parcel will also try to decrease its pressure. In doing so, it has to expand. If it has to expand, then it has to do some work. If it has to do some work, it will lose energy. If it loses energy, the temperature will drop down. This is the parcel's basic fundamental dynamics. Okay. Now I have already told that the process here is adiabatic, right? Okay, process here is adiabatic. Now I will use the first law of thermodynamics, which is the energy conservation. We all are familiar to first law of thermodynamics. We are all familiar with the first law of thermodynamics, that dq, these are all specific. So specific heat, that is heat per unit mass, heat change per unit mass, that will be equal to internal energy change per unit mass plus P d alpha, where alpha is the specific volume. Now we know that P alpha is equal to RT by ideal gas law. Right? P alpha is equal to RT. Now if we differentiate it, the P d alpha plus alpha dP is equal to RDT. Now what I do is that P d alpha is RDT minus alpha dP. Correct? Put that in this. What you get? dq is equal. Now this du is nothing but Cv dt. This is also known to us. So it will be Cv dt plus R dt minus alpha dP. Remember, this R is specific gas constant. Remember this. This is the specific gas constant. So for dry air, it will be Rd. For vapors, it will be Rv. Similarly, Cv for dry air will be Cvd. For vapor, it will be Cvv. Fine. Now, I can further write Cv plus R, can combine it because dt is common, minus alpha dq. So dq will be equal to Cv plus R is Cp, dt minus alpha dp. So this is another first law of thermodynamics, mostly used in the atmosphere. This is also first law. Okay, but you remember that H, enthalpy is U plus P alpha. So dH will be equal to du plus P d alpha plus alpha dP. Right? Now du can be written as T d phi, that phi is entropy, minus P d alpha plus P d alpha plus alpha dP. This is dH. So P d alpha can be chopped. Now T d phi is nothing but the dq as per the definition of the entropy. So this will be dH minus alpha dP. Now compare this equation and this equation. So dH will be equal to Cp dt. So this is not the heat, this is the enthalpy, change in enthalpy. Right? So this is the equation which we will use to derive the potential temperature. So I will come to this question. Before that, let us derive the potential temperature. Okay, so I will use that first law, dq is equal to Cp dt minus alpha dP. It's an adiabatic process, partial theory or approximation which we take, it's an adiabatic. So dq will be equal to 0. What will happen then? Cp dt minus alpha dP should be equal to 0. So Cp dt is equal alpha dP, right? So now Cp dt, alpha can be written as RT by P, again from the ideal gas law. Now Cp dt by T will be equal to R dP by P. Now this will be dt d by T will be R by Cp dP by P. Integrate it from where to where? From some T to theta and up to 1000 from some P. Okay, so it will be log of theta by T will be equal to R by Cp, which is a constant, log of 1000 by P. Right? So theta will be equal to T 1000 by P to the power R by Cp. Fine. For dry air, we just change this as Rd by Cpd. Now another thing, so what is this potential temperature? Suppose this is a surface and I have a parcel. This parcel is suppose here, okay, not here. This parcel is over here, and if I bring this parcel back to 1000 hectopascals, what will be its temperature? That is the potential temperature. So with respect to 1000, potential, anything potential, say potential energy, it has a reference point. Then you calculate what is the energy. Similarly, this 1000 hectopascals is the reference. So based on this reference, each level's potential temperature can be calculated. Say for this is for 700 hectopascals. Okay. For 600 hectopascals, suppose there is a parcel and it has some temperature T. Okay. Temperature is here. So this parcel is having some temperature T, this one, and pressure is known. Then we can find out what will be its temperature if we bring that parcel back to 1000 hectopascals. So with respect to 1000 hectopascals, what is the temperature of that parcel at 700 hectopascals with temperature something? So let us do a numerical to understand the concept fully. Okay. So what was the numerical? Calculate the potential temperature of the air parcel whose temperature at 700 hectopascal is 15 degrees Celsius. Again, in thermodynamics, never keep the Celsius scale, change it to Kelvin scale because there is a standard 288 Kelvin, right? Just use this potential temperature definition of the potential temperature. So theta will be equal to 288 into 1000 divided by 700 hectopascals. I have told these are all in hectopascals, and in ratio it will cancel. Now what is this RD by CP? Now what is RD? 287. What is CPD? We have just now calculated, it is 1005. So it comes out to be about 0.268. So this will be 0.268. Let us calculate how much it comes. So it will be 1000 by 700 to the power 0.268 into 288. So it comes out to be 316.8. Now 0.88 Kelvin is a wrong way of representation. Generally temperature is measured into one place of decimal, so it's 316.8 will be a correct answer. So this is the potential temperature. So a parcel which is in 700 hectopascal height with temperature 15 degrees Celsius, if we bring this parcel back to 1000 hectopascals, then its temperature will be 316.8 Kelvin. Or with respect to 1000 hectopascals height or surface, what is the temperature of the parcel at 700 hectopascals? So this is the potential temperature. Fine. This is done. Another is simple thing. Parcel of air has temperature minus 51 degrees Celsius at 250 hectopascals level. Find its potential temperature. Just formula based. So what is temperature? Minus 51 degrees Celsius plus 273. That comes out to be how much? Let me calculate. 273 minus 51. Oh sorry, 273 minus 51. 222. 222 Kelvin, right? Now pressure level is shown to be 250 hectopascals. Reference is set. Reference is always 1000. So theta, potential temperature, will be equal to T. The reference is fixed 1000 hectopascals. Divide by 250 where the pressure level where the parcel is there, and again consider it to be dry air when nothing is given. So T will be equal to 222. This will be 4 straight away. 0.268. Let's calculate how much it is. So it's 4 to the power 0.268, 1.44. into 222, about 321.8 Kelvin. So if a parcel from here, if it is compressed back to this 1000 MB level from 250 MB level with temperature minus 51 degrees Celsius, you will see that its temperature has become 321.8, is decreased. Sorry, increased from minus 51. Okay, fine. So the potential temperature concept is clear. Now another thing is the equivalent potential temperature. I will not derive the equivalent potential temperature, but I will tell you the what is the meaning of this equivalent potential temperature. You will get the derivation, entire derivation in the week 5 or week 4 lectures, and I think week 5 lectures you will get. But I will give you the insight of the equivalent potential temperature. And after I give this, there will be one numerical which I have to solve based on moist static energy and dry static energy. After that we will stop. Okay. So equivalent potential temperature. So we have seen what is potential temperature. That 1000 hectopascal level is the reference point. Anywhere, any pressure level where a parcel is there, if you bring or compress back to 1000 hectopascals, what is the temperature? That's all. But equivalent potential temperature is somewhat different. Now here, suppose there is a level where a parcel is present. Okay. Now, if this parcel is saturated, and not only that it is saturated means what? The vapors now are saturated vapors. These vapors now are saturated vapors. So what are these saturated vapors? Suppose this is a container and which is closed. Okay, some temperature is initially is there, some water is there here, and the air above is free. Now, if you keep the temperature like this, after sometimes you will see that if the rate of condensation, the equilibrium condition, the rate of condensation becomes rate of evaporation. So condensation, vapor molecule will condense and water molecule will evaporate at same rate, and that is nothing but the saturated vapors. So saturated vapors are also called as the equilibrium vapors. Okay, so these saturated vapors will be present. Now this saturated vapors is still in vapor phase. Now what happens is that as it goes further up, then there are some condensation nuclei where these vapors will be condensed. So you can see that there is a term minus LDWS. This DWS represent the, or minus LDWS represent the saturated vapors are decreasing and condensation is taking place. Now as it goes up, condensation droplets form. Now all the condensation droplets fall out. Okay, all the condensation droplet falls out. Remember, earlier in case of the parcel theory we have said that it's an adiabatic process, but now it is not adiabatic. Why? Because condensation droplets are falling out. So if condensation droplets are falling out, it is pseudo adiabatic. It's not adiabatic. Why? Very little amount of heat goes with the condensation droplets. When these condensation droplets are falling out, very little amount of heat is released. So that's why it is not a complete adiabatic, but a pseudo adiabatic. So condensation droplets falls out. Now if I take this parcel back to 1000 hectopascals level, that temperature it attains, that is known as the equivalent potential temperature, theta E. That is the equivalent potential temperature. And this entire process where a parcel becomes saturated. Saturated vapors are there. As it goes further up, saturated vapors, so saturated vapors turns to condensation droplets, and these condensation droplets immediately after forming drops out. Little heat goes out, and that's why it is pseudo adiabatic process. Now, in that pseudo adiabatic process, theta E remains constant. Why? Because all the saturated vapors has been converted into, so all saturated vapors, let us consider, all saturated vapors are being converted into condensation droplets. Now no further saturated vapors are left. So condensation droplets also falls out. Now entire heat which is present is here. Now if I bring back whatever the temperature was here, same temperature will be here, because no extra latent heat has come and there are no particles left within this air parcel which will take up the latent heat and becomes vapor again. So the theta E remains constant. The equivalent potential temperature will always remain constant in a pseudo adiabatic process, whereas in the adiabatic process, in the previous case, this potential temperature theta remains constant. So see, in this, say 250 MB minus 51 degrees Celsius, whatever the potential temperature for this parcel, if you bring back here the same parcel, not the other, if you see what is the pressure level and its temperature and you calculate the theta, it will come out to be the same. So entire process theta is constant. So for adiabatic process, theta is constant. For adiabatic, and for pseudo adiabatic process, theta E is constant. The equivalent potential temperature is constant, but the potential temperature will change here. So there is an expression, I think d theta by theta is tend to increase with dws with a minus, something like this is there, some ldws by some t cp maybe. So what is happening when the dws means the saturated vapors are decreasing? When the saturated vapors are decreasing, negative negative makes it a positive, d theta increases, potential temperature increases. So this is another point, potential temperature increases. Fine. So this is a concept of equivalent potential temperature. And well, and there is a, I think there is a formula for potential, equivalent potential temperature. You can see it from the what you call as that week 5 things. No such questions are there from that formulation, so I am not touched into it. Another is that some energetics in the atmosphere, and based on this we will do a question, very simple, just formula based stuff. Okay, so one is the dry static energy, the dry energy of the atmosphere, dry static energy. Okay, generally it decreases with height. This is DAC and this is your height. Okay, and this dry static energy DAC in joules per kg, generally it is written, it is CPT, the change in enthalpy, plus GZ. GZ is the geopotential. This is geopotential. How much amount of potential energy is required, or how much amount of work is to be done to take 1 kg of mass against the gravity. Geopotential. And this Z is geopotential height. Geopotential height. And CPDT, you know, is the enthalpy. Another is the moist static energy, where the moisture is also playing some role. Some energy is also due to the moisture. Okay. So what is that moist static energy? MAC in joules per kg will be equal to CPT, not DT, but CPT, not the enthalpy therefore, just CPT plus GZ plus LQ. Okay. CPT plus GZ plus LQ, and this is the extra term. So DAC plus LQ is nothing but MAC. Okay. And this Q is specific humidity. This Q is specific humidity. Fine. So this generally varies like this. Just a minute. I think I have made this thing wrong. This is dry static energy is not like this. Wait. Dry static energy is increasing. Is always increasing kind of, because you can see that T although decreases, but GZ is very high, so it generally tends to increase. And this moist static energy is like this. Fine. This is the moist static energy. Fine. Okay. Now, based on this, there is a simple question. At 500 hectopascals, if the temperature there is 2 degrees Celsius, or temperature is therefore calculated as 275 Kelvin, right? If the specific humidity Q is 0.001, because it is 1 grams per kg, what will be the dry static energy? What will be the moist static energy? So simple. Cp is known, L is known, surface pressure is 1000, but before that Z needs to be calculated. So how to calculate Z? So Z will be equal to RdT by G log of P naught by P. Gibbs symmetric equation. So calculate the Z or the delta Z, what you say, whatever Z. So this will be 287 dry atmosphere. T temperature is 275. Let's say for the entire column it's nearly approximately same, and divided by 9.81. Fine. Log of 1000 by 500, and that comes out to be nearly 54706.64 joules per kg. Oh, but this is, let us make it GZ. So G into this, the G and 9.81 cancel. So this will be joules per kg. Okay. So this is the potential energy. Fine. The geopotential. Now DAC is easy to calculate. That is nothing but CPT plus phi. So CPT is, you have to calculate. CP is 1004 into 275 plus 54706.64. And that comes out to be about 33806.64 joules per kg, or 330.81 kilojoules per kg, right? This is the amount of dry energy which is present. Oh, sorry. the moist energy, the moist static energy will be nothing but same CPT plus phi plus LQ. Just we need to calculate LQ now because DSE is already calculated. So 33806.64 plus 2.5 into 10 to the power 6 into 0.001, which will be very small. So 33806.64 plus it comes out to be 2500. You see, it's very small. So it comes out to be 333,306 joules per kg or 333.306 or 31 kilojoules per kg. So this is how the moist static energy is calculated and the dry static energy. So these are the energetics of the atmosphere. And so this is the last question which I have. And wait, let me see, something else is there. No, I think it's fine. Nothing is there. And this plot I will check and tell you that how this dry static energy varies with height. Okay. So here I stop. Nothing else is there, I think. No. Okay. Keep.
Okay, sir.
Okay.
Thank you.
Okay, bye. Good night. You have some question or?
Yes, sir. This slide is provide me.
You will get this slide. See, in the NPTEL, I have seen that there is a problem solving thing is given. So you just click in that, there will be a Google Sheet. So the YouTube video recording is also there and you will go to that link of the PPTs. So you will get there.
Okay, sir. Okay, thank you.
In your NPTEL thing, you will find wherever you are solving the assignments, getting the assignments, there in the left side, in the bottom side, you will get that problem solving link. So there you will find. Okay.
Okay, okay.
Okay.